Hello and welcome to my presentation about virtual product development with an SDM system. I'm demonstrating this by playing with Lego car models as an example. The whole thing about crash simulations using Lego models started when in 2017 ADC, which is a German consumer rating agency, and CT Computer Magazine showed this crash of a Lego Porsche model against an ODB barrier at full speed. And when they did that, they were asking the community what will happen. And at that time, we at Scale and also at Dynamo, we were thinking, who else, if not we, should be able to predict this with a simulation? However, we quickly realized that this is not as easy because if you download the CAD data, you see that this model consists of many parts and you have to model it in very fine detail to actually capture the physical effects of such a crash. However, I stuck with the idea to use Lego models for our SDM system to just demonstrate the capabilities of an SDM system. And I was starting to define all the goals and all the testing parameters. I uploaded the geometry of the car and defined also processes to automatically extract key performance indicators such as the level of destruction and the drag and the lift for aerodynamics from the actual model. So in the next slide, I will explain this a little bit more in detail on this small example. For example, if you have a simulation data management system, one thing which you can do at the beginning is define requirements. Requirements in terms of thresholds. For example, I have here the requirement for the level of destruction at a 20 km/h crash. And I defined here that the level of destruction should be below 20%. The level of destruction means in how many parts the model gets disassembled with respect to the total amount of parts. So if the level of destruction is 100, it means each brick is by its own after the actual crash. So I decided 20% would be good, between 20 and 24% would be acceptable, and above 24% is bad and is not good. My goal is below 20%. And if you define these requirements up front, you can define them for all different kinds of key performance indicators and for all of your project. Then at the end, you have the ability to monitor if your results are actually good with respect to your requirements. And can also define a milestone plan for all your vehicles. And by clicking on the different milestones, you can see how good your performance indicators have been performing at that time. Okay, but before we can actually get to monitor results and everything, we have to actually create the model. And I started creating the model by importing Lego CAD data. If you look around on the internet, you'll find that there are many different CAD systems that you can use to actually create your own model, Lego models. So if you are interested in that, just look out these resources. And it's actually a lot of fun to create Lego CAD models, even with smaller childs, to be honest. And what I did here, I imported the CAD data actually into our SDM system. Obviously, if you have a PDM system in place, you probably would pull in the CAD data from the PDM system. But in my case, I just integrated the Lego CAD software with our SDM system so that I can work directly on the CAD data from within our SDM system and share the data with all my colleagues. And what we then did, we created a library for the meshed bricks, which you can see here. And this library then can be mounted in all the different Lego projects which I'm doing. And I do not have to repeat the meshing of the Lego bricks. I just mesh each Lego brick once, keep them in the library, and then I can use the Lego bricks in my Lego models. I do this by actually reading with a small script the CAD file extracting the positions of each Lego brick, and then I'm creating automatically LS-Dyna include transform cards to position the brick accordingly. And this way, it's pretty easy then to create the simulation directly on the CAD data. So this means actually I can change something in the Lego CAD file and run the simulation right away without having to mesh anything once I have this process in place. Once I had that in place, I also created in our SDM system lots of different load cases for different velocities like 10, 17, 20 kilometers per hour, or for different angles of impact, and also for different crash scenarios, obviously. And another thing is I integrated HPC resources. For example, if you want to run a simulation, you do not want to go to the file system and have to upload your data manually to the HPC system, but you just right-click on the run here, and then you choose remote assembly. And once you do that, a process is started which will actually submit the job, for example, on-premise at scale at our own HPC resources or into the cloud or to some provider. For example, for the bigger models, we had a collaboration with HLRS, which is a HPC resource provider in Stuttgart. And lately, we also wrote a connector to Rescale, so you can also just submit jobs to the cloud. Once the job has been run and the solving is complete, the data mostly gets also post-processed in the on the HPC resources. Videos are extracted, curves are extracted, key values are extracted, and everything is uploaded to the SDM system again. And then you can go into the SDM system, this time in a browser, click on like two simulation or on one simulation and one test result, and then you can compare them side by side. For example, here I uploaded a small test video of an actual crash test, which I filmed with my smartphone at that time in the slow motion mode. And I was able to compare that always to my newest simulation result. And this gave me the opportunity to play around with parameters which we did not really know, like friction, clamping forces, or numerical parameters. And we were able to actually validate the model. And with that, I had my demo case for our SDM system. But this was also the basis to start more complex challenges, because now I had a working process, and approaching the actual Porsche Lego model then was only a matter of meshing the 182 different bricks which were used in the Porsche car. And we also used our SDM system then to distribute the workload of meshing to different volunteers throughout all of our offices and all of the offices of Dynamo, to be precise. And by this, at some point, we were able to actually create the full vehicle crash model for the Lego Porsche model. And we validated this against the video footage which we had from YouTube. And that was the result. And as you can see, we already got pretty close with these results. The actual simulation is quite big, to be honest. It's about 20 million elements, finite, it's volume elements, and just 120 milliseconds of crash. You need almost a whole day if you're using 192 CPUs. Okay, and with this results, we then approached again the CT Computer Magazine and also ADC Consumer Rating Agency, and we were asking them if they would like to write a new story on simulation and how simulation can predict such scenarios. But they told us no, and they would only write something if we actually were able to predict some things and not to simulate something that we already saw. And they suggested that we do this scenario where the simulation is even bigger. So the Bugatti is a Lego model which is bigger than the Porsche. And the simulation should predict what's going to happen in the actual test. So the simulation was done without actually seeing any test footage. The test has not even been performed at that time. And it has 46 million elements. So this involves also quite a lot of data that you have to process. So the challenges are huge, actually, to get this kind of simulation through. However, we did, and with the simulation, they went to the test court, and actually they built the whole test again. And this is just one of the videos which you can see is already capturing the details very good. And we actually, yeah, I think we did it. So, okay. However, with this, the story of the SDM system does not end. For example, if you have all your data now in the SDM system, you can do multiple things with that. For example, as I explained earlier, I have the data in a parameterized form within the simulation data management system. And therefore, I can easily do a data analysis there. For example, I have a parameter for the velocity, I have a parameter for the offset to the barrier, I have a parameter for the angle. And then I can just send, let's say, 50 simulations. And once all the simulations are through and they are post-processed and they are imported back into the SDM system, I can use the web browser, select the tests I want to do the data analysis with, and can do things like showing a correlation matrix or doing a sensitivity studies or a trend analysis, which you can see here. And basically it says if I increase the speed, the level of destruction will increase, which is kind of obvious. What's not so obvious is that if I decrease the overlap with the barrier, so the lesser the overlap with the barrier is, the higher the level of destruction is. So you can actually do a lot of things with your simulation. Or you can also set up other simulation disciplines. So what you see here is a car-to-car crash simulation, which actually is linking two different projects of the cars together and using the output of that project, the cars, to create another kind of simulation. And what we also did on the same CAD data, we created a CFD process for evaluating the aerodynamics. And we used OpenFOAM as a solver here and a snappy hex mesh process where we actually can create the meshing for the CFD completely automatically. And this way we can actually perform a CFD simulation right away after changing something in the Lego CAD model. And also on the same data, perform the crash analysis. And we did also the post processing and key value extraction using ParaView in this time. So you can also go into your web browser and look at all the results, compare the different simulations that you did, the different variants. At the end, there's another discipline which I implemented in our simulation data management, which is a rather exotic simulation discipline, which is rendering. Basically, rendering is only a simulation of how the light behaves. And for that, I used a solver called Blender. And within these Blender simulation, I'm referencing actually the D3 plot file, which is created in our Steiner simulation. So I'm kind of chaining two simulations within my simulation data management system together. And the cool thing about is once I've set up this process, I'm able to repeat the same rendering for each of the Lego simulations that I've been doing. And that's why you see all this rendered videos, because now for me it's actually easy to perform this kind of renderings. Okay, with this I'm at the end of my presentation. What I'm going to do in the future. Okay, I already received this green beauty for Christmas, and we already built this in our office. So I probably will do a simulation with this one as well, and I'm only 17 bricks away from having it meshed all, so you probably will see some simulation on that. What I also will do is I will try to implement more simulation disciplines. For example, I would really love to do powertrain simulation for simulating all the gears inside such a Lego model. And I would also love to do multi-body dynamic simulation. So I only have to get a license for ADAMS there. And what I also experimented already with is SPH, water splashing simulation, which are also a lot of fun. So I will keep having fun with these kind of simulation. There's one more thing to mention. We can provide these models for free. We license them by a Creative Commons license. However, it's primarily for non-commercial use. If you want to use them commercially for benchmarks or whatsoever, you can reach out to us, and we can also find some agreement. With this, I'm at the end of my presentation. Thank you for your attention. If you have any question, you can always reach out to us, and we will be happy to answer them.